Hi everyone! In this video we're going to be picking up where we left off on the week 5 notes, which was page 45 in your workbooks, and it was solving systems of equations algebraically. Okay, before we jump into how to solve these things algebraically, let's go back to what we did in the last video just for a quick little recap about what a system even is and how you would solve them graphically. So a system in this class means you're going to have two equations. And again, what we did in the last video is we solved them graphically, which means we would graph one line, we would graph the other line, and their answer would be where the two lines intersected. Okay, that is how you solve it graphically. To solve something algebraically means you're literally just going to do some algebra, and you're going to end up with the same answer. So there's two different methods for how you can solve a system of equations algebraically, but ultimately, you're going to end up with the same kind of answer. So I'm going to kind of just jump to this because it is so crucial that you know this. Remember that your answer should be a point. Your point is the answer to your system of equations, or in other words, that intersection point. So you always want your answer to be in the x comma y format. Okay, so like I said, there's two different methods we can use to solve a system algebraically, and it really depends what your setup is. So this one, it's even starred here. Okay, it says use this when you can easily substitute or plug in. So remember what substitution means. We've talked about it in previous videos. You can plug in a number for a letter or plug in a letter for a letter. It just means you can take something and plug it into what it represents in something else. To put it as vague as I possibly can. So in other words, it's like when you have a y equals or x equals setup. Okay, so if you have something given as y equals, that means you can substitute whatever it's equal to in for y. Or if you have, let's say, an x equals, you can plug in whatever x is equal to in for x, and so on. Whatever letter, it doesn't need to be x or y. That's just generally what you're going to see. Okay, so let's go through these steps piece by piece. Step one says to substitute one equation into the other for a variable. So that's the wording for it. As we do that, I'm going to show you how it's actually done, and then you can refer back to those steps later if needed. So like this says up here highlighted in red, you're going to use this method when you can easily substitute something in. So if you look right here, he's green. I have a y equals. In my second equation, I know what y is equal to. It tells me y is x plus 1. So what that means is I can take what this y is equal to and substitute it in to the other equation where I see a y. So I'm going to say that again because it is a lot. Okay. We have this y equals up here. In my second equation, it tells me that y is equal to x plus 1. If y is equal to x plus 1, that means that this side and this side are identical, depending on what x and y need to be to make them identical, but they are the same. So I can take this x plus 1, which is equal to y, and plug it into my other equation where I also see a y. So the way that's going to be written out is in place of this y right here, I'm going to write x plus 1, and the rest of the equation is going to come down. That's the whole idea for setting up substitution. Before moving on to the next step, why on earth would anybody go through that process? Here's why. We have these two equations, y equals 2x plus 5 and y equals x plus 1. Both of those equations have two variables. No matter what you do, whether you subtract the 2x over or you subtract this y over, no matter what manipulating you do to these two equations, you are always going to be stuck with an x and a y. If you have two variables, you can't get a numerical answer like we need no matter what you do. If you notice, by substituting in this x plus 1 in place of y, we're now left with this equation here, where there's only one variable. I know there's two x's, But we know how to solve this when there's two x's, especially when they're on opposite sides of the equation. We know what to do. There's no y here. That's the big gist of this entire substituting setup, is you just eliminated a letter so that you can now solve for x. Okay, so I'm going to solve this like I would solve any equation for x. And I'm just going to subtract this x over because I like to move the smaller of the two over. But remember, when they are on opposite sides of your equal sign, you have to do the opposite operation. So I'm going to subtract that x to move it over. So I ultimately cancel it on the left side. And when I combine these, keep in mind that is a 1x. 2x minus 1x will get me 1x. And the plus 5 comes down. Our goal here is to solve for x. So to get this x by itself, I have to first get rid of what's being added or subtracted, which is that plus 5. So I'm going to subtract 5 from both sides. And 1 minus 5 is a negative 4. I bring down my equals, and 1x is just x. If you do bring down the 1, you can divide by 1, but you'll end up getting that x is equal to negative 4 anyway. Now here's the big downfall with solving algebraically instead of graphically. You have to remember this idea right here, that the point, or that your answer, I should say, needs to be in that point x comma y format. So we did step 1 by substituting in the variable. That was this right here. Step 2, we already went and did. It says solve for the one variable in your new equation. So we solved for x. I know that's part of my answer. Step 3 says to use this variable in one of your equations to determine the other variable. So this step is going to be the same every time, which is rather nice. You can pick whichever of these two given equations in your original system is easiest and plug in that x is equal to negative 4. So I think the bottom one's easier, so I'm just going to rewrite it over here. Again, both of them will work. And then to find y, since you already know what x is, you can take that x value and plug it in right here. So in place of that, it's going to say y equals negative 4 plus 1. And look at how easy it is to solve for y. You just have to do what negative 4 plus 1 is, and negative 4 plus 1 is a negative 3. So I have an x, I have my y value, I just need to write it in that x comma y format. So my final answer is negative 4 comma negative 3. And that's it. Now we are going to practice that process again. But before we do, I want to talk about what the solution means, and I'm going to actually go back in our notes. So if you look at this equation, or system of equations that was given, it was y equals 2x plus 5 and y equals x plus 1. Go to the very beginning of your notes and look at the system we solved. Very first question we did. Y equals 2x plus 5 and y equals x plus 1. We just solved the exact same system algebraically that we solved graphically in the previous video. And notice your solution is the same. It's just that point where the two lines, if graphed, would intersect. So see right here, my solution was negative 4, negative 3. And here the solution is negative 4, negative 3. You're just doing it another way, specifically algebraically, because there's no grid to graph on, first of all, and the directions say to solve it using substitution. So you have to follow that method. Right, so let's go ahead and do another one. Solving system of equations algebraically continued. 174 says solve the following system of equations using substitution again. So literally that exact same method. I think the hardest part about it is probably the setup. But look, you would know you want to do substitution because of this right here. The y equals is given to you. It says that y is equal to 1 minus x. So where you see a y in the other equation, you're going to plug in its place what y is equal to, which is 1 minus x. Okay, if you need to hear that again, just rewind it. I know it's a lot to take in, and it's just the setup from there. Hopefully the rest of it really makes sense. I know the setup is hard. I'll tell you, this next method that we're going to go over is more commonly seen on tests and quizzes. So just still stick with me, because some people actually prefer this method, but we're going to get into another method if you're not a huge fan of this one. So what I need to do is rewrite that second equation, but in place of y, because I don't want two variables, I'm going to plug in what y is equal to in terms of x, which is 1 minus x. And then I also bring down the equals 9. So I'm really rewriting this entire second equation, but in place of y, I'm plugging in the 1 minus x that the other equation told me y was equal to. Now immediately in this problem setup, I see the distributive property. No matter what equation you are solving, if you see the distributive property, you want to do it first. So I'm going to distribute that 3 through. So the x plus comes down because only the 3 is being multiplied through. So 3 times 1 is going to get me 3. And 3 times a negative x is a negative 3x. And my equals 9 comes down. Now the setup for solving for x for this one is a little bit different, only because notice where your equal sign is and your two x's are on the same side of the equal sign. If they're on the same side, you just combine like terms. So 1x minus 3x is a negative 2x. Your plus 3 comes down and your equals 9. And you solve this like you solve any regular equation. To get x by itself, get rid of what's being added or subtracted first. So to undo plus 3, I'm going to subtract 3 from both sides. The negative 2x comes down, and 9 minus 3 is 6. Okay, now to get x by itself, last step here, it's being multiplied by negative 2. So to undo that, I'm going to divide both sides by negative 2, and 6 divided by negative 2 is a negative 3. Okay, now I know it's tempting to think that you're done at this point because you got this answer. You solved for x, you feel good, but you're not done because remember your answer needs to be in that x comma y format. Think about it in terms of graphing it. When you graph a line, you graph the other line, they intersect at a point. Okay, so now I need to plug this x equals negative 3 in for whichever equation looks easier. Truthfully, I think the top one looks easier, but if you plug it into either, you will get the same answer. If you want to try the other one, just test it out, see if you should believe me or not. I promise it'll work. But definitely take the easier one just to make it easier on yourself. So when I go to plug this in, the y stays, the equals, the 1, and the minus all come down. But in place of x, I have to plug in a negative 3. Notice that even though it looks funny, there is a double negative there because the minus in the equation and the negative in the solution. And that double negative will become a plus. So all you have left to do is 1 plus 3 and y is equal to 4. And remember, those are just the two pieces, so your final solution, or the intersection point, if you will, would be negative 3 comma 4. So what that means graphically is if you were to graph this line and graph this line on the same grid, this is where they would intersect. Okay, so that's really the gist of substitution. You take what one of your equations is equal to, and you want that y equals or x equals set up so you can easily just substitute it in for that letter in your other equation. That would be substitution. Elimination has a different setup. Okay, so on the stars right here tells you the setup. It says you want to use this other method called elimination when your variables line up. Okay, when your variables line up, here's what I mean by that. Notice in just the first example, x is on top of x, y is on top of y, and the equals are on top of each other, and the numbers are like the constants. The numbers by themselves are right on top of each other. They're in the same setup where it goes x, then y, then equals, then number. That's how you know you want to do elimination, and that's often how you're going to see the systems that I give you on tests and quizzes. Okay, so when you have that set up, elimination, the method we're about to go over right now, is probably your better bet. The reason you can't do the reason the setup isn't ideal for substitution is because for substitution, you need to have one of these letters by itself. So you'd have to move that 3x over, divide by the -1. There's like prep work you need to do, whereas elimination, it's already set up for you. You don't have to do any prep work. It's good to go. Okay, so your first step is to make sure that those variables are lined up, and they are, so we're good to go. Okay, rather than reading through the steps, I'm going to kind of just try to explain it to you as best as I can. So your goal when you are solving a system with elimination is to ultimately eliminate one of your variables. Kind of like we did with substitution, where you plug in for y, all of a sudden you only have x's. You want to eliminate your variables, and you're going to do so by adding your equations together. So it's very easy once you see it as an example. I'm going to add these two equations together. What happens here when I add the two equations together, if you notice right here with 3x minus 3x, they cancel. 3x minus 3x is nothing. They completely cancel out. And then I continue adding. Next would be negative y, or negative 1y if you will. Minus 6y is a negative 7y. My equals comes down, and then 2 plus a negative 9 is negative 7. Simply adding the two equations together completely eliminated my x term, and now I can solve this. We have the same issue that we had in the last system example where you have an x and you have a y in two equations. You have to eliminate one of your variables in order to solve for anything. So that's why adding them together eliminates one of those variables, and now I can solve this for y. So to get y by itself, since it's being multiplied by negative 7, I'm going to divide both sides by negative 7. So the y comes down, and then negative 7 divided by negative 7 is a positive 1. Now what is kind of nice about going over this method right now is you know you're not done, because again, same reason as the last one. Your answer needs to be written as a point, x comma y, and right now we only have a y value. So you pick whichever of the two equations you think looks easier. I personally think the top one has less going on. So I'm going to take that 3x minus y equals 2. But in place of the y, I'm going to plug in 1. So you're still kind of using substitution to find your other variable, but this is that elimination process to start. So my 3x comes down. In place of y, I plug in a 1, and that's equal to 2. And now this is very easily solvable. To get x by itself, you get rid of what's being added or subtracted first. So undoing minus 1, I'm going to add 1 to both sides. So I get that 3x is equal to 3. And then to get rid of that 3 that's being multiplied to the x, I divide both sides by 3, and I get that x is also equal to 1. Okay, that definitely won't always happen with elimination. It just happened to happen this time. And then I write my answer as 1, comma 1, which tells me that if I were to graph both of these lines, that 1, 1 would be where they intersect. That's my solution. Okay, so that's the gist of elimination. You want to add your equations together, and in doing so, you want one of your variables to get eliminated. Okay, now the problem with elimination is oftentimes you're not going to be given this beautiful setup in the red right here, where they just were set up to cancel that way. If you look at number 176, if I go to add these equations together right now, I get 4x minus 1y, and neither of my variables canceled, and I'm not closer to solving this. So if that's the case, and more often than not it will be, you have to do some manipulation to make a variable cancel. So what I mean by that is right now, I'm going to try and cancel the x. Up here in my first equation, I have a positive 3x. What would I have to add to a positive 3x to make it completely cancel? Hopefully you're thinking a negative 3. A positive 3 will cancel with a negative 3. So ultimately what we're thinking here is I need to have a negative 3 in front of this x so that when I add these together, they will cancel. Now I can't just put a negative 3 there. What I can do is multiply a negative 3 through. Now notice where I put my parentheses. I put it around the whole darn thing. This is kind of a weird looking situation because we very rarely put parentheses on opposite sides of an equal sign. The only reason I'm doing that is because you do want to distribute across the whole thing, because what you do to one side, you have to do to the other. If you multiply the left side of this equation by -3, to hold that equality, you have to also multiply the right side by -3. Okay, and again, we're multiplying by that -3 through this whole thing so that it will end up canceling. So I'm going to rewrite that top equation just to keep my work organized. Again, I just took that equation and rewrote it. That's all we did. And then I distribute that -3 through. So -3 times x is a -3x. -3 times positive 2y is a -6y. The equal sign comes down when you're distributing over it. And -3 times a positive 3 is a -9. Now notice what we have here. Now that we've multiplied that -3 through, when I go to add these two equations together, I have elimination. My 3x minus 3x will completely eliminate, and I'm good to solve for y. So when I continue this problem, -1y minus 6y is a -7y, and 2 plus a -9 is a -7. Okay, you may or may not recognize it at this point, but this from here on out, actually from this here, is the exact same equations that we had in the last problem. I gave you the same question twice because I really wanted you to see that this right here, given to you, ready to be eliminated, will more often be given to you like this, where you have to figure out what you need to multiply it by to make it eliminate. So from here on, it is the same as number 175. So I'm not going to make you go through the works again, but that's the whole idea of elimination, is this manipulation here to make something cancel. So let's work with another one. This one needs to be manipulated as well. If you remember the first step we went through with elimination, elimination only works when your terms are lined up. Remember, x over x, y over y, equals over equals, and number over number. If you look in this case, I have x over, there we go. I have x over x, my equals are here, my y's are here, and then my numbers are on the end. So notice this one is wrong. The top one is yellow, red, blue, green, and the other one is yellow, blue, red, green. So that's not going to work out. We need to change the order for elimination to work. So to do that, what I'm going to do is subtract the 2y over to the left side. So watch what happens when I do that. My first equation becomes 5x minus 2y equals 8 because these cancel. And then when I bring down my second equation, they're lined up now. So notice the difference. I have my x's now, my y's, my equals, and my numbers. Everything is lined up. So that one mini step needs to be taken first. And now we're good to start elimination. So you want to try and see if you can add them right off the bat. Unfortunately, when I add my x's, they don't cancel. And when I add my y's, they don't cancel. So I need to do some manipulating first, like I already said. Now here's what's hard about this one versus the last one. The last one we had a 3 here, so I knew that would cancel with a -3. For this one we have a 5 here. I know that would cancel with a -5, so really you want this number to be a -5. But you can't multiply 3 by any nice number to turn it into a -5. So that's just not going to work. You can try to eliminate your y's, so let's look at that now. Okay, down here I have a -7, which means I want this to be a +7. There's no nice number I can multiply 2 by to turn it into a +7. So we've got a bit of an issue here. The issue, I'm going to solve it completely with you by using a shortcut. Okay, once I teach people this shortcut, they instantly love the elimination method. It will work every time, even with the last 2 examples that we did, the shortcut always works. Okay, so for the shortcut, I'm actually going to show it to you first, and then I'll write it out in words off to the side for you so we can so you can refer to it later. Okay, but the shortcut is going to be set up like this. You know you have elimination set up here because, again, you have your x, y equals number. When you have that set up, if you want to jump straight into the shortcut, which most people do, you put parentheses around both of your equations. This always works. Always works. Okay. So I put parentheses around both of my equations, and now what I'm going to do is I'm going to take this number in the front of x, put it here, take this number in the front of my other x, switch it up here, and notice what I just did. When I go to distribute this 3 through, this is going to get me a 15x, and so on. We'll do the rest in a minute. When I distribute this 5 through, it's also going to get me a 15x. Shortcut always works. The only other thing we need to include here is the fact that these 15x and 15x being identical won't cancel. You need one of them to be negative. It does not matter which one you make negative, as long as one of them is, so that ultimately they end up canceling. So I know that's a lot, but the shortcut, very easy, works every single time. I'm going to make the 3 negative. Again, it doesn't matter which one you make negative, as long as one of them is negative and one of them is positive. By doing the shortcut, you're always going to have opposites here, and they'll always cancel. So your shortcut is to flip your first 2 coefficients, which is the number in front of the x. So when I say flip them, I mean to do this thing right here where the 3 goes there and the 5 goes there. It's kind of hard to put into words, which is why I wanted to show you first. So you're going to flip your first 2 coefficients, those numbers in front of x. To distribute through to your other equation. And then you want to also make sure one is made negative. Okay, the whole reason that one of them needs to be negative is so that it cancels. Hard to put into words. I hope that kind of helps you. We'll do a bunch more examples like this so you get a better idea of the process of the shortcut. Okay. Before even moving on, I'll show you up here. When we had 3x minus y equals 2 and x plus 2y equals 3, if I did the shortcut, I'd put parentheses around both of them. I'd take this number here, bring it down, this number here, which is a 1, and put it up, and then make one of them negative. And notice we actually have the same thing. This one is a little bit easier because if you were to distribute a 1/3 of this top, it wouldn't change it at all. So it's literally the exact same thing, but you don't have to think about what this number needs to be. The method works for the shortcut all the time. Okay, so finishing out, now that I have the shortcut set up, I'm good to distribute through. So on top, -3 times 5x, and again, I'm right here. That's going to be a negative 15x. -3 times a negative 2y is a plus 6y. And -3 times a positive 8 is a negative 24. Make sure you bring down that equal sign before it. You're distributing through this bottom equation. The 5 distributed to the 3x is a positive 15x, which is perfect setup. I continue distributing. 5 times negative 7y is a negative 35y. And 5 times that negative 1, bringing down my equals, is a negative 5. Now that I did that shortcut and I distributed everything through, I can add my 2 equations together and my x's will cancel. So when I add my y's together, 6 plus a negative 35y, be very careful. or use your calculator, is a negative 29y. When you're adding the two equations together, your equal sign comes down, and negative 24 plus a negative 5 is a negative 29. That is a heck of a lot easier to solve now. To get y by itself, I just divide by the negative 29 on both sides so that these cancel, and I get y is equal to negative 29 divided by negative 29 is just 1. Now do remember that we are not done. Okay, you need an x comma y as your answer. So you can pick whichever of your original two equations you think is easier looking. I'm going to pick the top one. So 5x minus 2y is equal to 8. Remember, I'm doing this so that I can solve for x. Now that I know what y is, all I have to do is plug in y, and I'll easily be able to find x now. So 5x minus 2 times 1 equals 8. Okay, I'm going to simplify this first. So 5x minus 2 times 1 is 2 equals 8. And now I'm in that normal setup where you get rid of what's being added or subtracted first. So I'm going to add 2 to both sides. I get 5x is equal to 10. And then x is being multiplied by 5. So I divide both sides by 5 and I get that x is equal to 2. And now that I know what x and y are, I can write it as x comma y, which is 2 comma 1. This shortcut will help you so much. If you like the other way better of like figuring out what number would work, absolutely go for that. For this one, there was no other way to do it other than the shortcut. The shortcut 100% will always work. Okay, some word problems. We're in functions and modeling math in real world scenarios. So we're working with systems of equations in word problems. So 178, I'm just going to read it to you. It says, Franco and Carol went to a bakery to buy desserts. Franco bought 3 packages of cupcakes and 2 packages of brownies for $19. Carol bought 2 packages of cupcakes and 4 packages of brownies for $24. Let x equal the price of 1 package of cupcakes and y equal the price of 1 package of brownies. Before we even dig into writing these equations, I want you to somewhere state this off to the side a little bit simpler. So x is the price for cupcakes. Got to do it at least a couple times in each video. So x is the price for cupcakes. And y is the price for brownies. Okay, so that's that whole highlighted sentence simplified. Part A says to write a system, which again means 2, of equations that describes the given situation. Okay, so I have to write 2 equations based on what was given. If you read carefully, there's 2 different equations written out in words here. First is that Franco bought 3 packages of cupcakes and 2 packages of brownies for $19. Your other equation is going to be that Carol bought 2 packages of cupcakes and 4 packages of brownies for $24. So your first equation is going to be all about Franco. Okay, so think about how this would need to be written. If Franco bought 3 packages of cupcakes and the price of cupcakes is represented by X, to figure out how much money was spent on cupcakes, you would multiply the price of the cupcake, which is X, times how many packages it was. So 3X is going to represent the 3 packages of cupcakes price. And he also bought, so in addition to that, he bought 2 packages of brownies. Brownies cost Y dollars, so I would take that 2 packages and multiply it by what the cost of brownies is, which is Y. So 2 times Y. And when we add those 2 prices together, he spent a total, so equals, of $19. Okay, so that's Franco. Take a second. You can pause it if you want to, but I'll just pause for a minute. To write out the equation for Carol. pause the video if you need more time, but for Carol, it's really the same setup of the sentence. She bought 2 packages of cupcakes, and cupcakes is X, so that's going to be 2X to represent how much she spent on the 2 packages of cupcakes. And she bought 4 packages of brownies, so same idea, 4 times the cost of a pack of brownies, and altogether she spent $24. Okay, now part B says determine algebraically. So algebraically means you can use substitution or elimination. It's up to you. But determine algebraically the exact cost of 1 package of cupcakes and the exact cost of 1 package of brownies in dollars and cents. So think about what they're asking you. That's why I really wanted you to put this information here. It's really just asking you to solve for X and Y, right? Because it says find the exact cost of 1 package of cupcakes, that's X, and the exact cost of 1 package of brownies, that's Y. Okay, but in word problems, they're not going to say find X and Y. It's going to ask you for what they represent. So AKA solve for X and Y, but we're finding the cost of cupcakes and brownies packages. And we have to do it algebraically. So what I'm going to do first is just rewrite this system here. And I recommend you do the same. So just take a second to rewrite that system for part B. Then we're going to go through and solve it. Now your first decision here is to choose between substitution and elimination, and it's all based on your setup. Notice my X is on top of my X, Y over Y equals number. This is an elimination setup. It doesn't mean you can't do substitution. If you wanted to do substitution, you'd have to solve for either of the variables and then plug whatever you get that it's equal to into the other one. I promise it is a lot more work if you want to get it into the other form. When it's set up for elimination, I highly recommend elimination. So I'm going to walk you through the not shortcut first, and then I'm ultimately going to do it using the shortcut. Okay, so if you're the kind of person that doesn't want to use that shortcut, it's up to you, by all means. You want to look for some kind of pattern in the numbers so that you can turn them into another number. Like for example, if this is a 3, I need this to be a -3, and I can't multiply 2 by anything to become a -3, so that's out of the question. It's not going to work. For the y's, however, I have this as a +4. This would need to be a -4. You can easily turn that into a -4 by multiplying this top equation by a -2. Watch what happens when I do that. Okay, when I distribute this -2 through, I get -6x minus 4y equals 2 times 19, which is -38. Okay, when I bring down this next equation, left it exactly how it was, notice these can be added together and my y's would cancel, and I'd easily be able to solve for x. If you think you like that mentality of thinking, go for it, finish that problem as is. If you are the kind of person that's like, forget it, I don't want to have to think, I just want to use the shortcut, you would recognize that this is elimination and do the setup for elimination immediately with the 2 sets of parentheses. And then you take this number, put it here, take this number and put it here, and make one of them negative. It does not matter which one. Okay, so see the difference in the setup. Substitution, you have a lot less distributing to do. I'm sorry, I didn't mean to say substitution. Apparently I've been doing videos too long. With not the shortcut. There's a lot less distributing to do, but there's more thinking to be done in the beginning. If you're really not comfortable with that thought process that I just went through with figuring out this needs to be a -2, just do the shortcut, flip-flop these numbers, make one of them negative, works every time. So I'm going to finish it out that way. If you want to do the other way, it is in my answer key posted on Blackboard, so you can check your work that way if you'd like. So when I distribute this through, -2 times 3x is going to be a -6x. -2 times +2y is going to be a -4y. And -2 times a +19 is -38. So we really already did that. But using the shortcut, I'm going to distribute through the other one now. So +3 gets distributed through to make that x cancel out. 3 times 2x is a positive 6x, and those are all set to cancel. Now when I add, these will go away. Keep distributing through. 3 times 4y is a plus 12y. And remember that 3 gets distributed through to the 24. Do not forget it. That'll get me a 72. The biggest mistake people make with elimination is they only multiply through to the left side and they forget about the right side. But remember, what you do to one side, you have to do to the other. So if you don't do it to the other, your whole answer will be wrong. So make sure you distribute through the whole thing. That's another reason I like the shortcut, is it gets you in the habit of just putting these parentheses around to start, and that way you don't forget these numbers over here. Okay, we did the shortcut, so now when I add these together, one of my variables is going to eliminate, which is perfect. So negative 4y plus 12y is going to get me 8y. Your equal sign comes down when you're adding equations together, and a negative 38 plus 72 is going to be 34. Okay, now you might be a little ahead of me here. And thinking that you're not going to get a nice number when you divide by 8. Stick with me. 8 is being multiplied by the y. So to solve this for y, I'm going to just divide both sides by 8. And when you do that, you get an answer of 4.25. Now, so far up to this point, we've gotten nice answers. And what I mean by that is whole numbers. Okay, we've gotten like just an answer of 4. We haven't really seen decimals. But think about what your variables represent in this word problem. That's like that making sense of a problem thing that we've been talking about for a while now. If y is equal to 4.25 and y represents the cost of a pack of brownies, does that number make sense? That's what you want to be asking yourself. The answer is yes. Okay, so the part of this answer here is going to be that a pack of brownies costs $4.25 or $4.25. That is part of your answer. It's half of it, actually. Now, even though it's a word problem, it's really the same kind of process. I now need to use that y value I just found and plug it in so that I can find x, or the price of a pack of cupcakes. So it doesn't matter which equation you use. I'll use the top one. Looks easier to me. And to find x, I'm going to plug in what I just found for y in place of y. So the 3x stays, the plus 2 stays, but 2 is being multiplied by y, so in place of y, I'm going to plug in $4.25, and I bring down the equals 19. Simplify this down so you have a nicer looking equation. So 2 times 4.25 is just going to be 8.5. No, we haven't really done a lot of solving equations with decimals. It's the same process. This is that standard setup where to get x by itself, you get rid of what's being added or subtracted first. So I am going to get rid of that plus 8.5 by subtracting 8.5 from both sides. That'll make these cancel out. Even though it's a decimal, it's the same process. And then 19 minus 8.5 is 10.5. And then we're almost done. To get x by itself, I have to get rid of that times 3. So I'm going to do the opposite and divide both sides by 3. And I get that x is equal to 3.5. Which again, think of it in terms of the problem. That represents the cost of cupcakes. And it does make sense. So that means that a pack of cupcakes costs $3.50. And that answers my question. It is a word problem, so you should go back and just make sure you've answered what it was asking. Figure out the exact cost of one package of cupcakes and the exact package of one pack of brownies in dollars and cents. So we are good to go. We answered the question all right here. Brownies are $4.25 and cupcakes are $3.50. Now, when you are solving this, let's say like I did something wrong along the way and I got that x was equal to negative 27. Okay, pulled a random number out of nowhere. Negative 27 does not make sense to represent the cost of a pack of cupcakes. That's that being mindful thing that we talked about with word problems. The answer needs to make sense. First of all, it's not going to cost you negative money. And $27 is kind of a lot for cupcakes. If it's got like $100 or something, you should know you're probably not on the right track. Especially if the totals, like let's say we did get 27. The total up here was $19 or $24 and they bought more than one pack. So that just wouldn't make sense. Okay, so think logically about your answers when we're working with word problems. It'll help you out big time. Okay, and then the code word for today's video is Jello, Jello. So go ahead and write that down so you have it accessible when you go to work on your quiz. All right, the next word problem we're going to do is actually dealing with inequalities, less thans and greater thans, and it's graphically. This graph looks crazy. Just stick with me. It won't be as bad as it seems. Okay, so the word problem says, the Real Good Cinema is conducting a mathematical study. In its theater, there are 200 seats. Adult tickets cost $12.50 and child tickets cost $6.25. The cinema's goal is to sell at least $1,500 worth of tickets for the theater. Okay, part A says, write a system of inequalities that can be used to find the possible combinations of adult tickets X and child tickets Y that would satisfy the cinema's goals. So a couple things I want to point out. It's asking us to write a system again, which means 2. And it gave us variables. It says that X represents adult tickets and Y represents child tickets. And this step isn't necessary to write out what they are. I just think it looks a lot easier when you write it off to the side rather than it being written in here. So X represents the number of adult tickets. Y represents the number of child tickets. So they're selling these tickets for, I imagine, a show. It doesn't specifically say. Okay, but it does tell you how much each type of ticket costs. So if you think about it, an adult ticket costs $12.50 and you're selling X many adult tickets. Let's say that we sold 10 adult tickets. How would you find out how much money you're making? You would multiply them together. So $12.50 is how much it costs for an adult ticket. So $12.50 times X is going to tell us how much money we made based on the X amount of tickets that were sold. Now, in addition to that, they also sold some child tickets. The child tickets were $6.25 each, and they sold Y of them. However many Y is, we don't know. That's what we're trying to figure out. But it's going to be 6.25 times Y to ultimately tell me how much money was spent for child's tickets. Okay, so far in the word problem, let's just kind of dig deeper into it. We've used that adult tickets are $12.50 and that children's tickets were $6.25. Now, when we do this math right here, we already talked about it, but let's talk about it again real quick. $12.50 times the amount of tickets you buy will tell you how much money was earned for adult tickets. And this piece right here, $6.25 times the amount of child tickets sold will tell you how much money was made on child's tickets. So to simplify this down, we have money plus money. If in life, in any problem, not even thinking about this at all, money plus money is going to equal money, right? Money plus money equals money. So your total here is going to be the other money value, which was $1,500, and that was given as a total. It said the cinema's goal is to sell at least $1,500 worth of tickets. If they want to sell at least $1,500, that's your total or more. Think about what at least means. At least $1,500 means that or higher. Okay, so if we're thinking about at least, meaning $1,500 or more, that means we want the amount of money we make in tickets to be greater than or less than $1,500. What symbol should go here as an inequality? I know it's tough with the wording. It's going to be a greater than or equal to. At least sounds like less, and I know that. But when you think about what at least means, it means at least $1,500 aka 1,500 or more. So you want this side to be equal to 1,500 or higher. So equal to 1,500 or higher means a greater than or equal to symbol. Now that inequality is awesome, and I've used 3 of the 4 given numbers. Now do keep in mind, we were supposed to write a system of equations. So far I've only written 1. The only number we haven't used so far in the problem was that there are 200 seats. So think about the constraints on this theater. Okay, the equation that we wrote so far is about their goal for the money they wanted to make. So this plus this should equal 1,500 or more for them to meet their goal. They want to make at least $1,500, and this is how they can do it. But there's only 200 seats in the theater. So if let's say they sold 1,000 seats for each of these, they definitely make more than 1,500. But the problem is they can't sell more than that many seats because there's only 200 seats available. So that's why you need another inequality to show that other constraint. Restraint? So the 200 seats, think about the tickets. X represents the adult tickets. Y represents child tickets. If I add together the amount of adult tickets to the amount of child's tickets, my total should be 200 or what? Hopefully you're saying 200 or less. If I add the amount of tickets for adults and children, it has to be hopefully equal to 200, but it can't be greater than 200. You can't sell more tickets than the number of seats you have. So x plus y is less than or equal to 200 is your other inequality. And now we have a system. All right, so we are good to graph this now, which looks icky because there's decimals, but stick with me. This is about as tough as a system is going to get. So if you've got this, you've got them all. Okay, the first one I'm just going to rewrite over here is 1250x plus 6.25y is greater than or equal to 1,500. Okay, problem here is I can't graph it right now because it's not in y equals mx plus b form. So you have to get that y by itself first by getting rid of what's being added or subtracted first, which is that positive 1250x. So I'm going to subtract 1250x from both sides, making this cancel over here. My 6.25y is going to come down. My greater than or equal to comes down. And just like all the other ones, even though these are bigger numbers and there's decimals involved, these are not like terms. So you bring it down exactly how you see it, which is 1,500 minus 12.50x. I know it's kind of tight in there. Okay, last step to get y by itself, it's being multiplied by 6.25, so I'm going to divide everything by 6.25. So now these cancel out. We're gonna end up with more space now. So y is greater than or equal to 1,500 divided by 6.25 is going to be a nice number. Plug it in your calculator if you need to. It's 240. And negative 12.50 divided by 6.25 is just a negative 2, and the x comes down. This equation is so much nicer than the original one we wrote for sure. But you have to write that original to start because you use the information that was given to get it. Okay, so this is mx plus b form, so I'm going to state what m and b are. B is 240, the number by itself, and m is negative 2, but I want it to be a fraction, so it's over a 1. And when I rise over run, it's going to be down to right 1. Now you have to be very careful here. I am going to start at 240, but if you're going down to right 1, look at your scale here. This is 10. This is 10. 10. It's increasing by an increment of 10. So look at your x-axis. Also 10, 10, 10. The x-axis is going up by 10s as well. So in this case, because the x and the y-axis are both increasing by a scale of 10, going down 2 boxes and right 1 box is equivalent to going down 20, right 10. Down 20, right 10. And those are proportional to going down 2, right 1. So you can, in this case, just go with the boxes down 2, right 1. Because both of the scales both of the axes are going up by the same scale. Okay, so just do that down 2, right 1 pattern the whole way. And then think, is it a solid or a dashed? Our symbol is greater than or equal to. The or equal to tells me it's going to be a solid line when I connect it. So, whoopsie. So when I connect it, here's my solid line. I'm not going to use my ruler for this one, and I'll tell you why. Whoa. Okay, solid line because of the or equal to, and for this one, you're not going to put arrows on the end of it. The reason for that is, if I draw an arrow to continue this way, that means your y-axis is going down, but y represents the amount of child tickets, and anything lower than this 0 is going to be a negative amount of tickets, which is not possible. So in this case, the graph does not continue down, and using that same mentality, it's not going to continue to the left either, because that would be to the left of 0 here, and that would be negative adult tickets. Sorry, I forgot what X was. Then we can't have negative adult tickets. There's no arrows on this graph at all. Okay, so it's a solid, and it's also a greater than, which means I'm going to shade up. Okay, so I know this one's a lot of shading. We're just going to shade it up towards the top of the graph. Trying to be nice and neat here, but it's such a big graph. If you need more time with that one, absolutely pause the video. I'm going to jump to the next equation, which is x plus y is less than or equal to 200. So this one's a lot easier to get into y equals mx plus b form. To get that y by itself, I'm going to subtract x from both sides. So I get y is less than or equal to, and when I combine these, not combine them, sorry, I would bring them down because I can't combine them. It'd be 200 minus x. And you're already in y equals mx plus b form, just like that. So I'm going to state what m and b are. B is 200, the number by itself. And m is the number in front of x, which is a negative 1. And I want to turn it into a fraction, so I put it over a 1. Okay, so what this is telling me is I'm going to start at 200, and I'm going to go down 1, right 1, down 1, right 1. I know that's super annoying, but go for it. Down 1, right 1, down 1, right 1. Hopefully you notice you hit that other line almost right away. Don't connect it before you think about whether it's solid or dashed. Oh, snap. There we go. Down 1, right 1, all the way. So we'll give you a minute to do that. All right, now this symbol is a less than or equal to, which means it's also going to be a solid line. But because it's less than, you're going to shade down. Okay, so a solid line shaded down. And this line also does not have any arrows at the end for the same reason that the other one didn't, is you can't have negative ticket values. It's a solid line and shaded down. just to help organize this graph a little bit, I'm going to label, remember up here we said that X was adult tickets and Y was child tickets? I'm going to put that on my graph. So my Y-axis is child tickets and my X-axis is adult tickets. Knowing which one is which, specifically when just looking at the graph, will help with the next part of this question. Okay, so now that we have this graph, part C is asking us, Martha claims that selling 30 adult tickets and 80 child tickets will result in meeting the cinema's goal. Remember, their goal was to make at least $1,500 while still staying under 200 seats or 200 tickets sold. Is she correct? So 30 adult tickets, remember adult tickets is X, would mean that there's an X value of 30. And 80 child tickets means there would be a Y value of 80. So they're asking you if that point will meet their goal. So let's find that point on our graph. An X value of 30 is right here. Y value of 80 is right here. So the point 30, 80 is at that black dot right there. Does that meet their goal? So remember, their goal needs to work with both of our inequalities, the red and the blue. Where do they both work? Okay, they both work in the double shading, which is this yellow area I'm coloring in right now. This is where both criteria work, having less than 200 tickets sold or equal to, and making at least $1,500. 3080 is not in that double shaded area. So is she correct? That would be no. Explain using the graph would just be because 3080 is not in the double shading. Okay, because remember the double shading in the graph is where your solutions lie for both inequalities at the same time, meaning they meet the system. So because it's not in the double shading, it doesn't work. What might be a point that does work? Okay, literally any point in that yellow double shaded area. I'm going to pick this point right here. So a point that would work with their two restrictions, or goals I should say, would be 150, what's the Y value? 30. So that would mean 150 adult tickets sold, pairing up with 30 child tickets. Okay, I know it didn't ask that, but just to kind of help you understand where a point works and where a point wouldn't work, would be just like that. Okay, now that problem was a lot. I recommend taking like a little 5-minute pause before we go on to the next page, but I do want to tell you that a question like this will never be on a test or a quiz. It was just way too much for a certain problem, too much room for error. I would not give that to you. However, you might see a graph where you need to graph a system of inequalities or something like that. It's just not going to be to this level of difficulty. All right, so last page here is mixed review. What we're going to do, if you notice on this page, all three parts, A, B, and C, have the exact same system. We're going to solve the same system with all three methods that we learned. So first, let's start by reviewing graphically. To do it graphically, you just need to graph each of the equations. So I'm going to start with the first one, which is y plus 3x equals 7. We just went over a graphing one, so it should kind of be fresh in our minds, but luckily this one's an equation, so no shading, no worrying about dashed lines, just graphing. But remember, to graph, you need to be in y equals mx plus b form. So to get that y by itself, I'm going to get rid of the plus 3x by subtracting 3x from both sides. So I end up with y equals, remember these can't be combined, so I bring them down as is, 7 minus 3x. And I'm in mx plus b form. So m is the number in front of x, which is a negative 3. I put it over a 1. That tells me I'm going to go down 3, right 1, starting at b, which is 7. So go ahead and graph that. Hopefully you've really got a good handle on this now. You've graphed quite a few examples at this point. Again, it does not need to be solid or dashed. Don't even worry about it. Just connect it like you'd connect any old graph. And this one does have arrows on the end. We're not in that word problem scenario anymore. If you need more time, pause it. I'm just going to move on to the next one. So 2y plus x equals 4. I still need to get it in y equals mx plus b form. So I get rid of what's being added or subtracted first, which is that x. So to get rid of plus x, I'm going to subtract x from both sides. So my 2y comes down, my equals comes down, and this 4 minus x can't be combined, so I just bring it down as 4 minus x. This next step's a little bit trickier, but not too bad. To get rid of the 2 in front of the y, they're being multiplied, so I divide, divide, divide. So those 2's cancel, and I have y equals 4 divided by 2 is 2. And then this right here is a negative 1 divided by 2. That's going to stay a fraction, so you leave it as negative 1/2 and just bring your x down. So my m is the number in front of x, which is that negative 1/2. So it's okay that that's a fraction. I actually want it to be 1. And b is going to be 2. So I'm going to start graphing this at b of 2, where b is 2. And I'm going to rise down 1, run right 2. So starting at a y-intercept of 2, I go down 1, right 2, and I hit the other line right away. So down 1, right 2, just to finish off my graph. You do have to graph the whole line to show all of your work. Okay, so remember, just a solid line. These are not inequalities, so I don't have to worry about dashed or anything. Here's my other line. It's crazy how difficult our examples got, and now we're going back to just graphing 2 lines, and your solution is where those 2 intersect. So this solution would be 2, 1. Now, I just solved that equation, or that system of equations, graphically. If I continue on now and try to solve that same system of equations using substitution and elimination, I should end up with that same solution. So I'm going to go to elimination first. The only reason I'm doing elimination first is because it's in the elimination setup where y is over y, x over x equals number. So typically if you were given this example on a test or a quiz, you would want to do it with elimination. So I'm going to show you the shortcut and how it kind of connects to the other way. Shortcut is to put the parentheses around both of them. Take this number, which is a 1, and put it here. Take the 2 and put it on top and make one of them negative. So the shortcut, set up like this, is actually the same way as if you would have done it with the thinking first, not the shortcut way. Because if you distribute this 1 through, it's not going to do anything. So distributing that 1 through is completely pointless. What we're doing here is making this negative 2 go to the y, so it'll cancel with this positive 2. Okay, shortcut or the other way, both end up being the same for this one. I'm going to distribute that negative 2 through, so it's a negative 2y. Negative 2 times 3x is a negative 6x. And the equals comes down, and negative 2 times 7 is a negative 14. Okay, now again, I could pretend I'm distributing a positive 1 through, but it's not going to change anything. So I'm just going to bring down that second equation. Now the whole goal of elimination is to be able to add your 2 equations together and make one of your variables cancel, and I do. So that shortcut worked out. I continue adding. Negative 6x plus a 1x is negative 5x. And negative 14 plus 4 is a negative 10. To get x by itself, it's being multiplied by a negative 5, so I divide both sides by negative 5. My negative 5's cancel, and negative 10 divided by negative 5 is a positive 2. Now remember, that's not your final answer because your answer should always be in that x comma y format. So to find y, I'm going to pick whichever equation looks easier. Honestly, I think they're both about the same, so I'm just going to use the first one. And you take that x value and you plug it in where you see an x so that you can solve for y. So y plus 3 times 2 equals 7. When I simplify this, it's going to be y plus 6 equals 7. And then one last step to get y by itself. I'm going to get rid of the plus 6 by subtracting 6, and I get y by itself. 7 minus 6 is 1. So notice, when you write your answer as x comma y, the solution is 2 comma 1. Which, when we graphed it, the solution was also 2 comma 1. You should get the same solutions. It's just different ways of solving it. On a test or a quiz, if it specifically says to solve it graphically, you have to solve it graphically. An algebraic method would not work, or would not get you credit, I should say. It'll get you the answer, it won't get you full credit. If you are asked on a test or a quiz to solve it algebraically, either one of these methods will work, but you can't graph it. Only if you're given the directive to graph it can you graph it. Otherwise, it'll be algebraically, which is either B or C. So we just did elimination. If you were the kind of person that preferred the substitution method better, you would want to know how to convert it to that setup. So right now, like we already talked about, it's in that elimination setup. To convert this to a substitution setup, you'd have to solve for one of your variables. I'm just going to solve for y. Okay, so I'm going to take that top equation, which is y plus 3x equals 7, and I'm going to solve it for y so that I can substitute whatever I get in for y in the other equation. Okay, so to get y by itself, you would have to subtract 3x from both sides. So you get that y is equal to, and again, these can't combine, so I bring it down as 7 minus 3x. Okay, now look at what we have here. We just found out that y is equal to 7 minus 3x. So I'm going to take that, and I'm going to plug it into my other equation in place of y. All right, so here we go. This second equation is going to be 2 times, in place of y, I'm substituting in my other equation's value for y, which is 7 minus 3x, and then the rest comes down, plus x equals 4. This is the equation that has only x's in it now because I substituted in place of y, and now I can solve this for x. I'm just going to scoot it up here. So it's 2 times 7 minus 3x, just rewriting it. I don't have enough space down there. Okay, I see the distributive property, so I absolutely have to do that first. 2 times 7 is 14, and 2 times negative 3x is a minus 6x. You bring the rest down, always distribute first. For this one, I do have 2 x values, but notice they're both on the same side of my equal sign, my negative 6x and my plus x. When I combine those, I'm going to get a minus 5x, because that's a positive 1 there. Okay, to get x by itself, you get rid of what's being added or subtracted first. To get rid of that positive 14, I subtract 14 from both sides, and I end up with negative 5x is equal to negative 10. And then to get x by itself, it's being multiplied by negative 5, so I divide both sides by negative 5, and I get that x is equal to a positive 2. Now that probably looks very familiar to what we did in part C. And literally this to here is very, very similar. So we already know what the next step is going to be. If you were just doing substitution, I'm just going to kind of rewrite out the same step. But if you didn't know this step already, this is where you would go with it, because you only know what x is at this point. You would need to find out what y is by plugging in 2 for x. So y plus 3 times 2 equals 7. Again, just the same steps that we did in the last one. You get y equals 1, and your final solution is 2 comma 1. Okay, so the same system solved all 3 ways that we learned in this week of notes. Just to reiterate, if it says to solve it graphically, you'll be given a grid, and you would have to solve it using the graph by graphing each line and then finding their intersection point. And then for parts B and C, it typically depends on the setup. Elimination is what you would typically want to use if you have this setup, y, x equals number. Okay, but I'm glad we went over part B with the elimination setup. Substitution can be done if you're given the elimination setup. You just have to do this like beginning little prep step first. So it's really up to you which algebraic method you want to use, but you have to use one of these if it says algebraically, and you have to use graphically if it specifically says graphically. Okay, you are a systems expert now. If you have any questions, please feel free to reach out whenever, and good luck working on those practice problems from the homework.